Hello, Narnach here. Welcome back to TIS-100. It's been a while since I recorded. That was due to basically my recording software and TIS-100 not really liking each other after a video card driver update. But everything is better now, and in the meantime TIS-100 has actually progressed a little bit. The way that puzzles are evaluated is now different. So before, a puzzle would run once with a static dataset, and then after that it would run once with a random dataset, basically to just double check that you were not building your solution tailored specifically to work with the static dataset. They made some changes now, and rather than just one static dataset and a single random set, they now run your puzzle against 4 static datasets, so 4 predetermined datasets, and I think the slowest cycle time, the slowest runtime of those 4 is used as your score. So that means that for some puzzles that were depending on basically just the nature of the data, then the cycle count has been upped by a couple points. So previously perfect scores are now no longer possible due to puzzles being evaluated differently. And that's also the reason why Zachtronics resets the entire leaderboard. So today I will be looking at the interrupt handler, which is I think this is the 9th puzzle in the sequence. And I'm first going to jump into the simplest solution I could come up with. Basically, this is the first one I came up with, and it's the most straightforward one. So as a reference, I still have the old Reddit scores up here, but I'm not quite sure how well they apply anymore. But I'm going to show you anyway. So first, I'm just going to run through 201 cycles, 9 nodes, and 46 instructions. And this way we get the idle counts. And just even if you just ignore the code for a bit, I'm currently using the top 8 of the nodes and a single node on the bottom row. So that's 9 nodes in total. Sorry. So if you just analyze that for a bit, the most optimal solution would use the top 4 nodes, because those are all inputs. It used the bottom node and 1 connector node, so that's 6. In this case we all use 1 here, just to get the throughput a bit better. And that's why we use 9. Okay, so what are we doing here? Well, we are building an interrupt handler, which operates based on these 4 inputs. We just read the numbers, and basically we're looking for a sequence in the numbers. So if the numbers go 0, 0, 0, 0, 0, doesn't matter. The moment a 0 gets followed by a 1, that's the point where we emit the input number of the interrupt. So if this one flips from 0 to 1, we emit a 1. If this one flips from 0 to 1, we emit a 2. Here it's a 3, and there it's a 4. So basically we are on the output, we're signaling if none of the input handlers flipped. In that case we emit a 0. And otherwise, if one of them emits a number, or if one of them flips from 0 to 1, we emit that input's number. And 2 interrupts will never change in the same input cycle. That's very nice, because it allows us to make some assumptions about the code. So the first simplest way I came up with solving this is basically letting the top node, the node that reads the input, handle everything, and basically we transform it into a state machine, which has 2 states. A state of off, basically this is a sequence of zeros. As long as we are in a sequence of zeros, we keep in the state off, and every time we remain in this state, we emit a 0 down. It's basically to indicate nothing changed. The moment we get a 1 in, a number that's greater than 0, then we know, okay, we just flipped from 0 to 1. So that means we can trigger the interrupt, which means in this case we move the number 1 down. Here it's a 2, there's a 3, there's a 4. And after that we fall into a pattern that I call the on pattern. So basically that's a sequence of 1s, in which case, as long as we keep emitting the 1, nothing happens because it's not a transition, it's just a series of 1s, which still means we have to emit a 0 until we go back to 0. Then we reset and then we start looking again for a 1. So that's exactly what we do here. So we take the number here, we store it, we check, and then we emit a 0, because as long as we're in a sequence of 1s, we are in the off state, so we always know that we will not trigger the transition. And then we check if we have a number that's equal to 0, that means we moved from a 1 to a 0. So that means we once again have to start looking for a transition to a 1. So that means we jump to the off label and we basically transition to this state again. If that's not the case, then that means we still have a 1 and we jump back to the on and we just continue looking for a 0 to break out of the loop. So basically this is it's a pattern of 2 loops. One loop is just stuck in 0 looking for a 1. The moment we find a 1, we move over to another loop that's basically 1, 1, 1, 1, 1 until we find a 0, and then we break back to the 0 loop. And the moment we go from a 1 to a 0, nothing happens, we emit a 0. But the moment we go from a 0 to a 1, we emit a 1. So that's what this entire pattern is based on. It's an internal state machine. So that's why we don't have to track data in ACK. All we need to do is we take the input, we store it, and then we use the jump instructions to compare this value to basically see if it's a 1 or if it's a 0. So for each of these nodes we do that, and because we know that only one of the 4 inputs can switch from 0 to 1 at the same time, or none of them, so then we know, okay, the moment we trigger the interrupt, we can just emit the number, and the next line is responsible for just taking all the numbers that get emitted from the first line, and we just add them up. So this node, so this one moves its number to the right, this one adds the number from here and from the left and then sends the sum to the right, this one sends its number to the left, and this one adds the number that it receives from the top, the sum from the left and the number from the right, and sends it down. And why can we do that? Because we know 2 interrupts will never change at the same input cycle. So if interrupt 1 triggers, we know the other 3 are not going to trigger, so we know they are going to emit a 0 because the interrupt did not trigger. So that means if we add all the numbers, only the number that gets emitted as an interrupt will actually be the number that results as a sum, because we are adding 1 number and 3 zeros, or we are adding 4 zeros in case none of them triggers. Now we move it down. So this is the most basic solution. It has a very simple state machine. That's one layer, and then it has a sum layer, and it just moves the number down. So it's very easy to see what happens here. And as I said, it's 201 cycles. So what if we want to optimize this for node count? Then it gets a little messier, because then we basically have to do everything in the top layer. We have to do the checking, so we have the state machine with the off, the interrupt, and the on. And while we do that, we also have to pass through the numbers. So this one just works as before, because it doesn't have to pass through anything. Only difference is that rather than passing the numbers down, it passes it to the right. And this one, however, needs to combine the input from the left with its own output and move it on to the right. And there's an interesting trick I discovered here. We are summing things. 0 plus anything is anything, because 0 doesn't change the value. So rather than passing the number from the left always along and then just summing it off in some final location, we can't do that because we don't have the space in this node to do that. Because here you already see I had to get some labels out, had to use some JRO jumps, basically to create virtual extra space rather than having nicely organized code. This is horrible to read, but it works. So, and one of the reasons this works is because here I'm already combining numbers. Because you know that if this one would emit 0 to the right, then we can just take the number from the left and pass it through. That's the exact same as if we would add the number from the left to the 0 that was emitted here. That makes sense, right? So that means anytime we would have emitted a 0, so that's in this one and this location, we just take the number from the left and here and we move it over to the right. The only other place here is when we trigger the interrupt. And in that case, we know if this interrupt gets triggered, we know this interrupt did not get triggered. But it still emitted a 0 from the left, so we have to do something with it. So that's exactly what we do here. We take the number from the left and we store it in ACK. And after that, we send the number 2 along to indicate that input 2 was triggered. So input 4 is basically the same as input 1, but it's moving to the left rather than to the right. Input 3 has to combine inputs from both the left and the right side, and that's why it's so jumbled, because this one is already strapped for lines, and this one basically needs 3 extra lines. Because we need one line here to move the number from the right after moving the number from the left, and we send them both down. And that's in case we have a 0 here. The same happens here. This is basically where normally the label on would be. That's before this line. Because here it's up ACK. That also matches with this up ACK. So here, rather than... So here again, we take the number from the left and we send it down, and we take the number from the right and we send it down. And after that, we jump to equal 0. If the number is equal to 0, we jump to off. That's the same as here. And in this case, rather than doing a jump on, we do a 0 minus 4. So we jump 1, 2, 3, 4 steps back, which is the number, the line that I have in a comment labeled with on. So the 0 back to a line is basically the same as a jump to a label, but it uses one less coding line at the expense of just being worse to read. And after all of this node will always get 2 numbers. So it will take the number first number and add it to ACK, then we add it, and then we send the output down. And as expected, it's 6 nodes, but we take 279 instructions rather than the 202 we did before. And also, because we had to cram our code a bit, we have 45 instructions. Which is actually 1 less than here, but that's, of course, because it's already pretty long and we don't have multiple places where we're adding code. So, now the one that I've tried to optimize the most for cycles. And so this currently one is 175 cycles using 10 nodes and 48 instructions. So this is 26 cycles faster than the 201 that I started with. And I've had a couple of interesting results in the meantime, so I nibbled 3 off by adding some extra instructions and using an extra node. Basically just rearranging the addition logic. Because the fun thing is, the previous solution, or the first solution, I passed all the data through the middle lane down here. But that actually meant that the further we got, the more things were happening. And this one was 4 lines long because it needed to combine a number from the left and from the right and up and send it all down. So what I did now was basically combine these two numbers, just send them down, combine them in here, and then send it down. And the same for these two. So this number goes through here. This one only adds from up and left and then sends it down rather than to the right. So this way, we have a three-liner here, three-liner there. We send the data down. This one moves it to the right, and this one combines it once again. And this way we have another three-liner, which means the flow through is pretty efficient. That's also why there's only a 10% idle rather than that it's constrained at this point. And so that is what got me to 195 cycles, and that's where I had this setup for the top node. So we moved the up value to ACK to store it, then basically do a jump based on the value that we got. So if it's greater than 0, we jump to the interrupt, which emits the number of the node and automatically falls through to on. If it's not greater than 0, we would move to 0, or move a 0 down to indicate that we did not have a match, and then we would manually jump back to off. But the thing is, you are stuck a lot in this loop. So that always means you have to do this jump off, which is not the most efficient way to do it if you have to manually do this jump all the time. So I rearranged the code a little bit to basically favor the other default case. So in this case, we take the value and we store it, and then we check, is the number equal to 0? If so, we jump to the label called fail. So rather than looking for a success case, we look for the failure case and do a jump based on that. So that's the equivalent to this one. But the nice thing is about fail is that we do a move 0 down. So we send the output straight down, and then we implicitly fall through and go back to off. We don't need to jump to off. And if you can imagine, if you're stuck in that loop all the time, not having to jump back to your starting point is going to save you quite a lot of cycles. So that's a way. Once you apply it to all 4 of your input nodes, they stay relatively in sync, and that saves you about 20 cycles. So that's from 195 to 175. And I tried to see if I could apply the same thing to this loop, but that actually didn't really matter. So, oh, actually I already do that. That was the thing. So this one was already efficiently set up to basically have the same structure. So we take the number from up, we store it in ACK. Then if we're in a sequence of ones, we always know that we're not going to trigger an interrupt because we're in a 1. We can't trigger an interrupt if we're in a 1 series. So then we just preemptively emit a 0, and then we just do the single jump if greater than 0 back to on to basically do the loop. And otherwise we jump to off if it resets, and this doesn't happen that often. But you're always stuck with the jump, so it's not that great. But this is a way to get it down to 175. Previously, the Reddit score was 160 using all 11 nodes. So they also used this node for something, I don't know. But yeah, as I said, I tried experimenting a little bit with the loop. If you look at the numbers, I went from 195 to 175, so that's a decrease of 20 by just basically getting a single number out of the cycle that would trigger about half of the time. So if in some way you manage to get another number out of the cycle for 3/4 of the time, then you basically save yourself another 15 or so cycles. But I'm not sure if that's possible anymore. So for now, this is good enough, and this is nicely optimized enough. So that's for now. That has been everything I have had to say about the interrupt handler. So as usual, if you have found a better way to do it, or if you managed to get a faster cycle count, please do let me know in the comments, because it's interesting for me to know, but it's also just cool to know for your fellow players who might be reading the comments to see if there was a better way to do it. So, and with that, I'm thanking you very much for watching, and I will see you next time. Bye bye.